Okay. Okay. So today we're going to cover cut elimination. So for the first part, which I'll be teaching, we're going to do cut elimination for sequent calculus. So this is the kind of most basic cut elimination proof, and then the other fancier versions of cut elimination, and then built on top of this basic one, just for the sequent calculus. Okay, so I'm going to start by defining the sequent calculus, and it's mostly the same as what you saw last week, but there's a few kind of minor adjustments to make the theorems go a bit easier. So I'm going to go over these now. To do this. Okay, so the first point is that instead of going over all formulas, we're going to restrict to subclass formulas. So we restrict to class of formulas generated by implication, bottom, and for. So the only logical connectors that we have are implies and bottom, and the only quantifier we have is for all. And so then it's an exercise, if you like, to show that every formula is equivalent to one just using these quantifiers. Okay. Okay, so that's the first adjustment, and then the second one is that we're going to go over the rules of the sequent calculus. So there's fewer of them because we have fewer connectives, and there's kind of minor adjustments. So first will be ideal rule or identity rule. So the identity rule says that with no assumptions, we can derive sequent. We can write any sequence which has A on both sides. And so last week, this was for any formula A, but for this, for today, we want an extra side condition. So here, you had a side condition where A is an atomic. Atomic means that A is of the form P T1 up to Tn, where P is a relation symbol, and these Ti are terms. Okay. So I've shown a bit why this doesn't matter, but first I do the rest of the rules. So next we have implication. So implication left is the same as you saw last time. So this implication left says that given and B sub delta and gamma to A delta, we can learn the implication on the left. So this sequence implies media. Just on the right. So this is implies left rule. So the right rule is for today, it's going to be split into two different rules. So right left and right right. So the right left says that if we have the gamma, if you have the sequence with A on the left, then you can derive if A implies B on the right here. So this is the right left rule, and then right. Instead of having an A on the left here, we have a B on the right. So they want to be delta, and then again we are introducing A implies B on the right. So we have A implies B on the right here. Delta. So this is implies right. Like this. In rules are the same as you saw last time, but just restricted to restricted set of quantifiers. So so bottom is very easy. It's just so it only has the left rule. As well. So all is instance of A. So A, substitute T for X. So given this, we can derive a sequence which has 4 on the left. So 4x, A here. And delta, and then so this is for all left. And then we have all right. So if we can derive A on the right here. Right. So this has a side condition, which is important. So we give this x here, this variable x, we give it a special name. So we call an eigenvariable. Eigenvariable. Kind of recall the terminology, which I think you saw last week, if I'm correct. So these formulas on the above, on the top of the inference wall, which get eliminated, these are called minor. These ones which are written in orange, these are minor formulas. Some which get introduced, these are principal. Formulas. And then the other formulas, which may or may not overlap with the principal formulas, are just called side formulas. Okay. So there's one rule which is actually very important for today. Which is of course the cut rule. So so the cut rule says that if we have gamma A delta and then we can eliminate out the A, so we have this gamma delta. This is cut. And then so we call A the cut. Today is to take a derivation which might include cuts and show how to remove the cuts, get a derivation which doesn't use the cuts. So once you have a cut-free proof, it has various nice properties that assume we covered later. Okay, so we better check that this gives the same set of derivable sequence as before, as you saw last week. So do this in the sequence with A on both sides for the rule that we have is when A is atomic, but then we can derive it for all formulas. And moreover, the derivation is cut-free. Okay, so I won't give a complete proof for this or for anything, but the basic idea is to do this by induction on the formulas A. So, for example, if A is of the form B implies C, then, well, start again up here. So if A is equal to B implies C, then if it is is this sequence, and well, and we can just kind of work our way backwards. So so we see there's an implies on the left here. So let's say that this was maybe introduced with a left pull, an implies left pull, and that means that we need this assumption. So it should be C implies C delta. And then right here we have gamma B, C implies C delta. Okay. And then we ask, like, how could we have derived this? Well, we have well, we have implies and right, so let's use one of the right implications. So if I got this right, it's the right one we can use here. Just the inductive hypothesis now, because C is a smaller formula. And then we can do the same thing on the right-hand side. So this time we use right-left, but again we use an inductive hypothesis because B is a smaller formula. The remaining cases are left as an exercise, so I'll say this is proof now. Position is that we also split the implies right into two, so we have to show we can derive the original implies right rule from the two paths that we were given, and so we can. So the proposition is that we can admissible rule that given these assumptions, we can derive this sequence. So this is what you called implied right last time. And so the proof of this is, well, we start off with the assumption. And then we use implies right left, for example. And this gives us this sequence, where we've eliminated the A and put an implies on the right here. And then we just use the other implication to get implies this sequence with just A implies B and no B on the right here. Since this is an instance of the implies right rule. Okay. So now to work towards the cut-elimination proof, we need a few more definitions, which are going to basically so I'll just give these definitions. So given a derivation pi, we can define its height. So the height of a derivation pi is defined inductively. And so if pi is of the form, well, we have a bunch of assumptions which can, so a bunch of sub-derivations which I'm going to call pi I, deriving gamma I does y. Then the conclusion, let's say, is gamma delta. And we define, okay, so I want to call the height here, I want to call it h of pi. And then so h of pi is defined to be the maximum of the height of pi I plus 1. So if this has any assumptions at all, then it's going to be one higher than all of its assumptions, or all of its sub-derivations, if you like. But if it has no hypotheses, then it's just it can be high zero. So, for example, identity would be high zero. It's the derivation, if you like, and then we can also define a kind of measure of complexity of formulas, which we call rank. So, the rank of a formula, so the rank written like this, rank A of a and inductively on formulas, inductively. At bottom is 1. The rank of an atomic formula is defined to be the rank of A plus 1. So this is kind of some kind of measure of the depth of the formula, if you like. The depth of the logical connect is in quantified. We call this rank. So just as a remark, we noticed that in this earlier proof, I can actually add kind of one more kind of observation here that moreover the height of the derivation is less than or equal to check that if you like. So then we can use this to define a cut rank. So the cut rank of a cut, the cut which looks like this. Is by definition the rank of the cut formula. So the rank of the A zero here. And then and then we say that the natural number n is a cut bound for a pi if every cut rank in pi is strictly smaller than n. We can notice that the derivation is cut free if and only if 0 is a cut bound. Because if there's any cuts at all in the derivation, then it has to be some natural number, and so that has to be the cut rank. And then if 0 is a cut bound, it has to be a natural number less than 0, which is not possible. But I notice, however, that the cut bound is not measuring the number of cuts, but instead it's a measure of how complicated the cut formulas are. So, for example, we can make the cut bound of a derivation go down by, well, we don't have to actually delete a cut. Instead, we can keep the same number of cuts, but apply it to a simpler formula. But it's still the case that once you brought the cut bound all the way down to 0, then the derivation has to be cut through. So before going to the proof of the main lemma, we have a couple of important technical lemmas and a couple more definitions. Get these right, we need to so we have like an issue with free variable capture that we need to deal with. So I'll move through this now. So so definition, so a variable x appearing in a pi is if it occurs we actually also want to allow for the case where or if it appears it's bound in the usual sense as well. I think this almost would allow for this. Okay, so the point is we know that if we see a formula like this, then we're used to the fact that any x's appearing in A here are bound, but this is another notion of bound for derivations. And it says that if we have x appearing in the derivation, which could be free, but if it's appearing above an instance of all right, where x is an eigenvariable for the rule, then it's bound in the derivation. Bound, we say that it's free. So otherwise, we say that in the currently variable x, so I should say the occurrence of x in the derivation is bound or free if it's not bound. Define a notion of substitution for derivations. So we write pi of t substitute x or the result of three with t. And in order for this to kind of work technically, we kind of want this extra part that first of all we take any bound occurrences of x and to be different from x, so that so what we want to ensure is that any free variables occurring in t do not become bound after doing substitution. So it's sometimes called free variable capture. So this is after we labeling variables occurring in t. If we see them bound in the derivation, we have to relabel them first. This allows us to show the substitution lemma. So if pi is a derivation of gamma delta, pi of t replace x is a derivation of the again substituting t for x in the sequence. And then so I won't give a complete proof, but the idea is just that this is by induction. By induction on might, if you like. And the technical lemma is weakening. So if pi is a derivation, write gamma primed pi delta primed for result of gamma primed delta primed. Is after relabeling any bound variables occurring free in so definition. We have a corresponding lemma. So these both have names. So this one is called the weakening lemma, and the one from before is called the substitution. Lemma. Okay, and then so the weakening lemma says that just that this is a valid derivation. and it has the same height and same cut bounds as pi. Observation about having the same height and cut bounds. This is also true for the substitution lemma. So for the substitution lemma up here, so you have moreover gamma of 2 plus x has the same height and cut bounds as or like less than or equal to cut bounds. Yeah, well, okay. Every cut bound of gamma is the cut bound of the substitution. Sorry, this should be pi. Sorry, it's pi. Lemma called the inversion lemma. What is if pi the derivation of with all on the right, so the sequence like this. So of height h and cut bounds k, and there exists similar qualifications. Yeah, so I won't write this out, but it's just similar, but for gamma to n implies b. Uh, okay. N implies b plus one. So proof, I'm just going to prove one, and I'm just going to sketch the proof of one. So by induction on height, and so if for x a is a principal formula in the last inference step of pi, then the last inference step has to be like a full right, so it has to be of this one. where delta prime is not necessarily the same as delta, because delta primes might have for all x a in it, where delta does not. So that's a case that we have to deal with. And it turns out that the kind of way that we handle this technically is to notice that we only actually need to deal with the case where this happens. So in other words, without loss of generality, this delta prime in the last bit on the right in the last derivation here is equal to delta with all xa. So as I said, it might be that all xa is already in the delta prime here. But if it's not, we can add it in by weakening. So this is always true regardless of generality by weakening. And then so this gives us shorter derivation of gamma to a delta. And then so if all xa is not the principal formula in the last step, then the last step has to be of, well, it could be several different things, but they all fit into the same general template that will look a bit like this, where we have a bunch of hypotheses with for all x, a on the right, and then we derive gamma to all x a delta. And then so the idea is apply the inductive hypothesis to the sequence here, to gamma y to yi. Okay. So there's some extra cases that need to be dealt with, but I'm just going to leave those as exercise. And then, so this allows us to prove the really key lemma, which is called reduction lemma. Reduction lemma. So given derivations by 0 of gamma to the delta, and sorry, this is pi r, and then pi l, sorry, yeah, pi l of gamma into delta, and rank of A, cut bound for pi l and pi r. So we can find a derivation of gamma delta We have height less than or equal to the height, the sum of the two heights of the derivations are given, and we have a cut bound rank of A. Okay, so if we just wanted a derivation, we could apply the cut, but this would break this. This would make that the rank of A is no longer a cut bound because the cut rank would be a rank of A plus 1. So, so instead we have to do something a bit cleverer. And again, this is by induction, but this time it's by induction on the sum of the two heights. Cases, but I just quickly go through one case. A is a principal formula for the last step of both pi L and pi R. Be like various different things, but let's just do the universal constant because this turns out to be a key case. So let's say A is for XP. So the last step has to be of a particular form. It has to be pi L. It has to be of a particular form. It has to be a full left. So regardless of generality, it's of this form. So full X B B of T replace X delta goes to gamma full X delta. A shorter derivation of this sequence than pi L, and we still have the pi R from before. So we can apply the inductive hypothesis in height to this formula 1 and to this sequence 1 and to the original pi right 2. One and two gives us pi L primed, derivation of gamma B T implies X delta with cut rank less than or equals to the rank of A and it of pi R minus 1. Substitution and reckoning. Okay, and then we we apply the inversion lemma to right. Then and then I can also substitution and weakening, and then this gives us a gives a derivation of gamma to okay, and then plus this one. Okay, and then we okay, and then we can apply a cut. And then the cut gives a derivation of gamma to delta. Okay, and then so then the key point is the heights and the ranks kind of work, cut bounds work out, and then the key point is that the cut formula. So we do apply a cut here, but the cut formula is B rather than full XB. So we do have a good cut bound. And then there are kind of more cases, but I have to leave them in the face.
And we think this would probably be a good point to finish now, which is kind of a bit unfair because you've done all the hard work and I get the punchline. Anyway, so other questions for Andrew before we? A good 15-minute break, so let's make it a break until 25 past by the clock on the back wall. Okay. Okay. So thanks to Andrew for the first hour. I think I gave him a next to impossible job because I gave him very many pages of notes to cover in 1 hour, much more than I normally do. And he almost got all the way through, but we didn't quite get to theorem, which is what I want to start with, which is cut-elimination. So cut-elimination, we already saw in one form last week. It's a bit wonky. We saw that if we saw last week, if a sequent is derivable, then there's a cut-free derivation. Essentially, we're going to have the same result, but we've proved it using different techniques in that this is now being proved by looking at the proofs themselves and manipulating the proofs rather than going via the soundness and completeness theorems of first-order logic. And because we're proving it like that, although it's not explicitly stated, what we're going to get from this proof is an algorithm for removing cuts from a proof. So given a proof with cuts in, you have a number of quite complicated rewriting steps that you can go through a procedure, and eventually you'll get a proof without cuts. So cut elimination, we're going to have it as a corollary of a theorem, which is itself a consequence of the lemma, the reduction lemma, the main lemma. So the theorem is that if we have a sequent that has proof, let's see, proof, meaning a sequent calculus derivation pi, as Andrew was calling them, with cut bound k plus 1, for some natural number k, then we can reduce the cut bound to k. So we can eliminate all, so cut bound k plus 1, the most complex cuts have rank have rank at most k, and we can remove all the cuts of rank k, and that then gives us a proof with cut bound k. So then it also has a derivation proof, let's say, with cut bound k. And because we've got this information about the heights when we're removing the cuts, we can work out that the best height we can get in general is 2 to the power of the height of pi. And height, we get 2 to the power of the height of pi. And the corollary of that is, well, if we can remove the cuts of rank k, we can then remove the cuts of rank k minus 1, and so on. And we eventually go all the way down until we remove the cuts of rank 0, which are the cut monotonic formulas, and we end up with a cut bound of 0 and therefore a cut-free proof. So the corollary is if a sequent has a proof with cut bound k, then it has a cut-free proof of height. And here we want to iterate 2 to the height of pi as many times as we need to get from rank k, from bound k to bound 0. So we need to do that k times, so it's an iterated exponential. So we have height, this should be height less than equal to 2 to the h pi. We have here height less than equal to, I'm going to use this notation for the iterated exponential. 2 is the base, k is the number of times we're iterating, and the number we're iterating is the height of pi. So, so this is defined inductively by the 0th iterate of the exponential applied to x is x, and the n+1th iterate. So the n+1th iterate. Sorry, this is for any base b. Just to be general, applied to x is just b to the power of the iterate, the n-fold iterate. Okay, so the actual main cut elimination statement is the corollary. That obviously follows easily from the theorem. And the theorem is very easily proved from the lemma. So the lemma tells us if we've got the reduction lemma says if you've got 2 proofs whose cuts all have rank strictly less than k, then and we try to do a cut that has rank k, then in fact we don't need a cut of rank k, we can get by with cuts of rank strictly less than k. So to reduce the cut bound on a proof, you simply start off with a proof with lots of cuts of rank k, and you work from the topmost cut downwards. So the topmost one, the subderivations of that cut won't have any cuts of rank k in, so you can apply the reduction lemma to that and get a proof of the conclusion sequence that doesn't have any cuts of rank k, and then you go down to the next cut below, and you keep on doing that. So you remove the cuts of rank k from the top of the proof down, and if you just work out what's happening to the heights as you go along because of this sum here, you see that you get this exponential bound that just works out. And then that exponential bound here obviously implies the iterated exponential bound here. And in general, you can give examples that show that you cannot do better than an iterated exponential bound. So cut elimination is necessarily a very costly process, in a very complex process. Right. So, are there any questions on this syntactic approach to cut elimination? Because what I want to do next is switch to the application. And the application is part 2 of the lecture, which is the remaining material of the lecture. And this is to look at the consistency of Peano arithmetic. It sounds like it's something. Sounds like there's no reason for that to be related at all to cut elimination. But we'll see that one way of looking at it, cut elimination can be used to give a very informative proof of the consistency of Peano arithmetic. So firstly, is the consistency of Peano arithmetic an interesting mathematical question? Well, it's only interesting really because of Gödel's second incompleteness theorem. So by Gödel's second incompleteness theorem, we know that Peano arithmetic itself, so our standard theory of arithmetic, cannot prove, remember, in the lecture on Gödel's second incompleteness theorem, we have this notation for the consistency of Peano arithmetic. So it cannot be proved in Peano arithmetic itself. So we need some principles that go beyond arithmetic, beyond first order arithmetic. But that's not necessarily very scary, because we often in mathematics use principles that go beyond first order arithmetic. Like most of analysis cannot be expressed in first order arithmetic, for example. There are standard easy arguments that Peano arithmetic is consistent, and the easiest argument is in set theory. So let me just remind you of how we would prove that Peano arithmetic is consistent in set theory. And for this, it doesn't really matter too much about which axioms we take for set theory. Any decent set theory will be able to do this. So can somebody tell me how we prove the consistency of Peano arithmetic in set theory? Why is it obviously consistent?
The natural numbers in set theory validate the axioms of Peano arithmetic.
Yeah,
So
very
we
good.
get
Yeah,
an inconsistency in Peano arithmetic, we also get an inconsistency.
Yeah. very good. So the natural in set theory, we can construct the model, which is the set of natural numbers. The axioms are true in the set, and by the soundness theorem, if the axioms are true, any consequence of the axioms and anything we can prove from the axioms is true. So if we could prove false from the axioms of Peano arithmetic, false would need to be true in the standard model of arithmetic, and of course false is never true in any model. So there's a slightly careful wording of that in the notes, but I don't see the point in doing that in the lectures. So we'll just say N is a model of Peano arithmetic. So we could ask, why can't we formalize this in Peano arithmetic? Well, we don't have the set of natural numbers as an entity, so we can't construct an element of the universe that is our model to be able to reason with. But we could maybe back off a little bit from wanting that and just look at sort of weaker requirement of what's going on here, is that in order to show that we can't prove false in arithmetic, the one way we're using the natural numbers here in order to basically get the notion of truth of a sentence or truth of a formula in an environment interpreting its variables. And essentially, the argument is that the axioms of piano arithmetic are true, hence any consequence of the axioms will be true and false is not true. So rather than dealing with a model of piano arithmetic, we could say, well, maybe we can just formulate the notion of truth of a sentence or formula in arithmetic, and then we could try to prove in piano arithmetic that all the axioms of piano arithmetic are true. But we can't do that for a reason that I think you did in the exercise class a couple of weeks ago, which is by an application of the diagonalization lemma, you cannot, in the language of arithmetic, it is impossible to formulate a truth predicate, as it's called, for the language of arithmetic, in the language of arithmetic. So because of that, I think no similar argument can work in piano. Well, we know no argument can work in piano arithmetic if you have Gödel's result, but no similar argument can even be attempted in any approach that is based on a formal theory that only has the language of arithmetic, that only deals with the language of arithmetic. So no similar approach to consistency can be carried out in the language of arithmetic, even if we give ourselves some additional axioms on top of piano arithmetic, because we simply cannot formulate the concept of truth. Because formulate the notion of truth. A truth predicate. So as I said, this was something we did in the exercise class a couple of weeks ago, and this using the diagonal lemma of Gödel, and it's something that this was due to Tarski in the 1930s. He realized that you can't formalize you can't express a truth predicate in the language of arithmetic. So this is Tarski. So today we're now going to look at a different approach, which is very appealing. So we've got some axioms, and we want to show consistency. So we want to show that given the Hilbert proof system, which was our reference proof system at the start, given the proof system, we cannot find a proof of the false statement from the axioms of piano arithmetic. So the Hilbert proof system just has a few rules, and we've got essentially the notion of what it means to be a proof, which is just an algorithmically checkable notion. And one wonders if you could actually give an essentially combinatorial proof that you can't prove false. You can't find a proof of false by having some deep insight into the structure of proofs. And that's essentially what we're going to do today. We're going to translate Hilbert proofs into sequent calculus and then use a slightly more powerful, well, maybe not, use a variant of this cut-elimination argument to prove that cuts are then eliminable from proofs. And as a consequence of that, we're going to get that false is not provable by a purely combinatorial argument, in a sense. It's an interesting kind of combinatorial. I mean, a combinatorist probably wouldn't call it a combinatorial argument because it involves infinite combinatorics. But we'll see where those come from when we get to it. So the benefit of this approach is that it can be carried out in the language of arithmetic, but obviously not from the axioms of piano arithmetic, because we're not going to be able to prove consistency of piano arithmetic. But in carrying it out in the language of arithmetic, we're going to be able to pinpoint exactly what combinatorial principle is missing from the axioms of Peano arithmetic, and give ourselves a new axiom schema to add to Peano arithmetic, which allows us to prove the consistency of arithmetic. Okay, so we shall use sequent calculus to give I'm calling it a combinatorial proof. But it's about the combinatorics of proofs. So people call these proof-theoretic proof of the consistency of arithmetic. In doing so, we're going to, as I say, identify exactly what additional principle we need to add to Peano arithmetic in order to be able to get what is missing from Peano arithmetic. Now, like in Andrew's part, I have pages of notes. The notes, like last week, the notes aren't quite ready, so I haven't published them online. And I think I'm going to just. We don't want to go on too long today, so I'm just going to put a few choice points into the lecture. And when the notes are published online, you can then refer to the notes and to other references for more details. And maybe to give away the punchline of what's going to come, so as I say, we're going to use sequent calculus to give a proof-theoretic proof of the consistency of arithmetic and identify what's missing from Peano arithmetic. And we're going to see that what's missing is a form of transfinite induction. For those of you who've done some set theory or remember back to Logika and Logika from the first year, maybe didn't exactly do transfinite induction there, but you did well-founded induction in Logika and Logika. What we're going to see is that, so I'll remind you of what transfinite induction is when we come to it. We're going to see that con PA is provable from Peano arithmetic plus a principle called transfinite induction up to a special ordinal called epsilon zero. Now, I'm not assuming that everybody is familiar with transfinite induction and ordinals today. I'm going to try and just give it a very impressionistic account of how this works, and hopefully it'll maybe whet your appetite to look at some more details. So this part of the material from now on is not examinable, also in the oral exam. It's just not examinable material on the course. Cut-elimination is potentially examinable for those of you who want to get very good grades. So we're going to use sequent calculus. We need a sequent calculus that can deal with arithmetic. So far our sequent calculus, well, last week we had the equality rules, but today we didn't have equality. So the language of arithmetic has equality, but also, and more crucially, arithmetic also has some axioms that are not purely logical axioms, that namely the 6 axioms of Peano arithmetic plus the induction axiom. So how are we going to do that? Well, we do that in the following way. We construct a sequent calculus proof system that is particularly tailored to arithmetic. So we henceforth work with the language of arithmetic. So all formulas are going to be the language of arithmetic. And we're going to take the sequent calculus from Andrew's part of the lecture, which was already a modification of the sequent calculus from last week with this. So we had this, in Andrew's part of the lecture, we had this additional restriction that in the identity rule, the formulas, the crucial formula that appears both sides of the sequence is atomic. And we had the splitting of the implies right rule into the two rules, each one involving only one of the subformulas. We're now going to replace the identity rule with something else in order to deal with most of the axioms of arithmetic. So we're going to replace the identity rule with, we can derive a sequence where the gamma and delta are just weakenings. But we've got m formulas on the left and n formulas on the right that we're looking at. Sorry, I should have, in Andrew's color code, I should have put these in red because these are the principal formulas of the rule. But anyway, imagine those are in red. We can derive such a thing. So the U's and V's are atomic here. That's a side condition. We can derive this whenever it's the case that it's true in the natural numbers that for all x1 to xk, basically this implication from the U's to the V's is true. So the conjunction of the U's implies the disjunction of the V's. So that looks very suspicious. We're bringing the notion of arithmetic truth into the proof system. Nevertheless, this is going to be okay. We'll be able to formalize this because it only requires truth of quantifier-free formulas. And one can formalize the notion in arithmetic, one can formalize the truth of quantifier-free formulas. I'm not going to go over that, but you can think about how to do it. So this is actually a perfectly legitimate, it's not something we can actually apply in practice because we can't check it, but as a means of forming a mathematical argument, it's okay to have this. And the next modification we're going to make is even more strikingly departing from what we would expect a proof system to have. And that's we're going to replace the for all right rule, which allows us to conclude a sequence that has a universal quantifier on the right, with the following rule. Does anyone know what's coming? Maybe some people have read about these kind of things. In order to prove a sequence that has a universal quantifier on the right, well, we prove the case for 0, we prove the case for 1, we prove the case for 2, and we require that we prove infinitely many cases. So we need to prove the case for 0, so we stick, well, 0 is its own numeral. We need to prove the case for 1, so we stick 1 in. We need to prove the case for 2. So we have a rule with infinitely many premises.
Excuse me, is this maybe connected to omega consistency?
Don't know if it's connected to omega consistency, but it's connected to omega because we have omega many premises, and it is called the omega rule. And this is called the omega rule. It appears in various guises, but they're all called omega rule. So our proofs are very weird things now. They're no longer finite. We have infinitely many premises for this rule. We've got a condition that we can't algorithmically check here. To be a proof, so a proof is now an abstract object. It's a tree of rules that's branching locally according to the rules. We require it to be what's known as well-founded, which means any branch that you follow, so we've got a tree branching, any branch you follow from the conclusion up to potentially an axiom leaf, all branches must be finite. That's essentially what well-foundedness means. Okay. But we can't actually write the proofs down on paper. But these proofs are going to have the right mathematical structure that we can nicely analyze their behavior. But there is something very weird about this, because I don't know if anyone's noticed this proof system is very powerful. Does anyone, while I'm clearing the board, does anyone have an idea what I mean? So what can we prove? I don't. So actually we can prove every true sentence of arithmetic. So every sentence that's true in the natural numbers, we can prove it, because essentially here, so how do we prove that? So observation. I don't remember in the notes if I call it a theorem or a proposition, but anyway, let's call it an observation. For any sentence A, then if A is true in the natural numbers, then we can prove the sequent with A on the right is derivable. And if N is false in the if A is false in the natural numbers, then the sequent with A on the left is derivable. That's basically saying not A. And the proof is very simple, because to prove a universal quantifier, well, we simply have to verify all the instances, but they're all true. So by the induction hypothesis, we have proofs of those. More interesting for the universal quantifier on the left, because the universal quantifier on the left, we need to find a term instantiation. But if the sequent is true, in other words, the left-hand formula is false, then there exists a number that's a counterexample. So you simply choose that one, and you carry on the proof. You carry on the proof like that. So these are derivable, and the derivation has height less than equal to the rank of A. With derivable, so the height of the derivation is less than equal to the rank of A. You basically, every rule peels off one of the quantifiers or one of the connectives. The height of the derivation now is more interesting than it was before in the case of the sequent calculus in the first hour, because now we've got infinitely many premises. The height of an application of this rule, well, here we might have a derivation of height 1, here we might have a derivation of height 2, here we might have a derivation of height 3. So if we want to give a notion of height to the whole derivation together, well, we're going to take the supremum of all of the successors of all those heights, but that's no longer a natural number, and this is where ordinals come in. So for those who don't know about ordinals, all you need, I'm not going to be too technical about it, but essentially it's just a way of counting beyond into infinity and beyond. So after you get to the end of the natural numbers, you go to omega, then you go to omega plus 1, and you keep on counting, then you get to omega times 2, and so on. And you can always find, you've got a sequence of ordinals, you can always find a supremum of them. So the height is defined as well, it's literally defined as the smallest ordinal that's strictly greater than the heights of all the subderivations. So I'm not going to write down the formula for the height, but that's how it's defined. Now, one thing about the proofs one gets in this way is that there's kind of potentially no real pattern to them. You're using the fact that the formula is true to find the proof, and a formula might be true for very arbitrary reasons, just because we know lots of things are very hard to prove, and we don't know whether the existential witnesses to negation, to false universal statements, we don't know how to find them. So somehow this is not very informative, but the way we're going to use the proof system is using a different approach, which is, so this is what happens if a formula is true. If a formula is provable in Peano Arithmetic, well, it turns out we can use the structure of the proof of Peano Arithmetic to give ourselves a proof that has a pattern to it. So here we get proofs that maybe have no patterns. They're just kind of very hard to understand the structure. They're very low in height. But it turns out if we have a proof from Peano Arithmetic, we get a proof with we get a derivation in secant calculus that has a definite pattern to it. In order to do this, we have to use infinite heights of proofs. And then we can cut-eliminate on those proofs, which has the same blowing up, the same feature of blowing up the height of proofs, just as it did in the finite case. And we end up with a very, very high cut-free, high in terms of having a high height, cut-free proof of the sequence we wanted to prove. So the two things are, if PA proves A, then we can find a derivation of sequent with A on the right with a nice pattern to it of height. Well, actually, we can always get away with, we don't have to go very high. So omega is the first infinite number, omega times 2. For those of you who know about ordinals, multiplication of ordinals, well, for those of you who don't know, multiplication of ordinals is not commutative. Omega times 2 is the interesting way of doubling. And we always get a derivation of height strictly less than omega times 2 for a theorem of Peano Arithmetic. So this is the first thing.
Excuse me, would such a proof be well-founded? Didn't you require proofs to be well-founded?
So whenever you can give it so we require it to be well-founded, and that allows us to give it an ordinal height. It can be given an ordinal height if and only if it's well-founded. Okay. I mean, I don't want to get, as I said, I don't want to get too much into the technicalities of ordinals. And then, so this is with cuts. And then we can eliminate the cuts and we'll get the consistency of Peano Arithmetic from that. So want a very long lecture today. There are a lot of details, and I'm going to make just a choice about what to show you. I'll do one thing. We'll then have a 10-minute break, and then we'll go into the last hour. And in the last hour, I'll just do a brief summary, and then there's also going to be the course questionnaire for you to fill in for those of you who managed to stay to the end. So the one thing I want to do before the break, I mean, we started again at 25 past, so it's reasonable to have a bit more time before the break. So the one thing I want to do is give you an idea of how we find this infinite proof for something corresponding to, we got a proof in Peano Arithmetic in the Hilbert system. Well, we saw last week how to simulate the Hilbert system. We didn't see how to get the equality rules, but actually the equality rules follow from this replacement for the identity axiom. So that's nice. The main axioms of Peano Arithmetic also follow from that generalization of the identity axiom, the first 6 axioms. So that's nice. So the really interesting thing is what happens to the induction axiom. So this is just a little hint, a little idea about what happens here. I want to show how we derive the induction axiom. So the induction axiom is, of course, a schema. So we want to derive any instance of the induction schema. So the induction axiom is derived by, well, it's the obvious derivation. The induction axiom, well, I'm not going to put it as a single formula. I'll put it in a sequent form from which it's easy to then apply a few more rules to get it to a single formula. So if we've got a with 0 substituted for the variable x, and we've got the other premise of an induction that if a holds for x, it holds for the successor of x, we want to prove this sequence that for all x, a, x. Rub that off. So, I mean, the obvious thing to do is to apply the omega rule here to derive the universal quantifier. So that means we need to be able to prove for every n, we need to be able to prove this formula with n substituted for x, with the numeral n substituted for x. Okay. So here, this is how I'm going to write applications of the omega rule. We've got infinitely many premises here. So these are indexed by the natural numbers n. And what I want to show, the point is that we can always find these proofs pi n, and there's a natural pattern to them. Well, when I was saying we get derivations of infinite height that have a nice pattern. And in the end, when we formalize it in the language of arithmetic, having the pattern means the whole proof can be coded up in a recursive function, in a computable function. But never mind about that for now. So here, pi 0 is obvious because pi 0 is just an instance of the identity rule. We've got a0 on the left and a0 on the right. And pi n plus 1 is constructed from pi n by, well, we use pi n to get, so this is defining pi n plus 1. So pi n gives us a derivation of the sequent with an in the conclusion. So that's pi n. But again, by a version of the identity rule, well, actually, let me just write out exactly what we want. It's very easy to find a derivation of this. Because we're restricting the axiom to atomic formulas, you can, the derivation of this has height something like 2 times the complexity of a plus 1 or something like that. I don't quite remember. The derivation of this, which is kind of very intuitive, because here we've got a universal quantifier, here we've got some instantiation of the universal quantifier on the left-hand side of the implication on the left, and it's not surprising. It's just a few inference rules we can derive the right-hand side of that. And then what we do to this is we cut the AN. Okay, I mean, strictly speaking, weaken this as well, so I put those have the same delta on the right, but never mind about that. We cut the AN out, and we get what we want, the conclusion we want. So and we see this inductive construction of these proofs here gives us all the premises for the omega rule. And it's kind of very intuitive, because essentially what we're doing is we're saying to get the premises, we're using the fact that A0 is true, and to get the nth premise, we apply the induction hypothesis by means of using a cut to effect it, the right number of times to go up from 0 to A of n. Okay. And so hopefully this gives you kind of feeling for how we get an infinite derivation with a pattern in it for the most interesting action of Peano arithmetic. Okay, so we haven't caught up any time here, so so how about a 10-minute break and we start again at 20 past? Is that okay? Yeah. Are there any questions? Okay, so now that we've got a way of encoding proofs in Peano arithmetic, namely Hilbert proofs. So this was the Hilbert proof derivability relation as proofs with infinite height, but with nice patterns in them. Then these proofs are certainly making use of cut. As you might remember, whenever we did a modus ponens in the Hilbert system, we needed to use a cut. And also the proof of the induction formulas certainly made use of cuts too. So we have plenty of cuts in here. So we're going to see if we eliminate cuts, then we can prove consistency. And there are some details in how one eliminates cuts, but I'm going to skip them. I just want to write down the main lemmas to say how the lemmas change from the ones that Andrew gave you in the first hour. So the first main lemma was the reduction lemma. And in our case, this becomes the following. So if we have, they've got a derivation of the sequence with an A on the left. And by the way, I should clarify in Andrew's part, because somebody asked about this, when we use this notation, the concluding sequent is assumed to be part of pi L. So this notation, so pi L means, this doesn't just mean that part of the derivation above this. This is a name for the whole derivation, including the concluding sequent. And that was important in the definition of the height of a proof. So let's put it like this: given proofs of things that look like a cut, things that look like we could apply a cut. Cut rank. So cut bound A. So they don't have any cuts of complexity A. Then we can find a derivation of the cut of the sequent we would get from a cut. without using a cut of rank A, so we can find such a derivation that still has cut bound, still has A as its still has the rank of A as its cut bound. So we can find a derivation of gamma delta with cut bound A, the rank of A, still. So we've only cut on smaller formulas and height. And now, in the previous case, we had height, the sum of the heights. In this case, we have infinite proofs. Well, we have an addition operation on ordinals, which some of you may know is a non-commutative operation. The correct thing to use here is a commutative version of addition, which is called the Hessenberg sum, or the natural sum of ordinals. And as I say, I'm not going to go into all the ordinal parts in details, just, this is the, I won't even write it down, but this is the Hessenberg sum of ordinals. It's an appropriate addition of ordinals. But it's basically the correct analog of the reduction lemma before. And given this, the cut elimination theorem and corollary have exactly the same statements as before. That is, if the highest, if you've got cut rank k plus 1, then you can find a derivation with cut rank k of height at most 2 to the height of the original derivation. And if you've got cut rank k, you can eliminate all cuts and get cut rank of the iterated exponential iterated k times of 2 to the 2 to the 2 to the 2 to the 2 of the height of the original derivation. So the theorem and corollary, I won't write them down again, have the same formulation as before. The only difference is the heights are now infinite, they're measured in ordinals, as before. There is one little detail to mention, which is these results actually only apply to derivations that don't have any free variables in them. So that means all the formulas in all the sequence are sentences. Because we got rid of the for all right rule, which crucially used a variable, an eigenvariable, and replaced it with the omega rule, which instead of using an eigenvariable, used closed term instances by substituting numerals. And if you've got a derivation that's got some variables in, you can get another derivation without any free variables simply by substituting, say, 0 for all the free variables. That may have a different concluding sequence because you may have substituted some variables in the concluding sequence. You still get a derivation. Okay, so technicality. The above results, I call them sentential derivations. So every formula occurring in the derivation is a sentence. For sentential derivations. Sentential. Okay, so lots of details have necessarily been skipped over when you can. For those of you who like this sort of thing, which may be none of you, you are welcome to peruse the 30 pages of lecture notes that will be put on the course web page in due course when they're finished, which as I've said, they're not quite due today. I want to just say two more things about it. So the first one is, so this is the cut elimination, the theorem and the corollary. We want to do the final corollary, which is of course what we were aiming for. PA is consistent. So how does it follow from what we've done? So the proof is now very easy at a high level. So suppose PA is not consistent, so you can derive false in the Hilbert system. So then we have a proof then we have a sequent proof. Of height less than omega 2 of sequent that just has false on the right. So that was by our lemma about converting the Hilbert system proofs to sequent proofs. One other thing I should have remarked, we've been talking about the cut bound. Because we've got infinite proofs, actually it's not necessarily the case that a proof will have a finite cut bound, because you could have, in the different premises of the omega rule, you could use sort of arbitrarily high cuts if you wanted to. But, and this should have been said at the time, when we convert a Hilbert proof to a sequent proof, the highest cut rank we use is the rank of the most complex formula that occurs in the Hilbert proof. So we do have a finite cut bound on this proof. So of cut bound K for some finite K. Moreover, because there are no variables in the concluding sequent, we substitute out all the variables in the proof and we get a sentential proof of the same sequent. Okay? All the free variables in the proof go away, we simply substitute 0. So let's say we have a sentential sequent proof here. Sentential. Okay, so we now apply cut elimination. We eliminate cuts and get a cut-free proof of false sequent of height, some iterated exponential, which when you calculate it is basically, although it started off with a 2, when you get 2 to the power of omega 2, that becomes omega squared, and you calculate things, and this may not be exactly the right thing, but you can get it as some powers of omega, where this is like, let's say, less than that, but this might be k plus 1 or something. It doesn't really matter. Let's put k plus 17 in, and then it's probably a safe statement. Anyway, we have some height, quite high height on the bound. Okay, but what will a cut-free proof of false look like? What rule can we possibly use to derive false in the cut-free proof? You can't. There is simply no rule that has, every rule has some formula it's working with on the bottom of the rule, and the only one that has a false in works with false on the left, not on the right. So there is clearly no cut-free proof of. Okay. So that's a proof that, of course, we can't formalize in Peano Arithmetic, because we can't prove, assuming Peano Arithmetic is consistent, we cannot prove consistency in Peano Arithmetic. However, we can actually formalize quite a lot of it in Peano Arithmetic. So the infinite proofs can be coded up by using indices for computable functions to encode the function that takes you from a path through the proof to enough information about the rule that's applied at that point in the proof to be able so that you're basically encoding an infinite proof as a function that takes you to the nodes in the proof and then gives you the information about what's at the node. So you can do that, and then you can try to prove these lemmas. And all these lemmas are proved. So in the case of Andrew's part of the lecture, they were all proved by induction on the height of derivations. In our case, they're again proved by induction on the height of derivations, but the height of the derivation is an ordinal. So we need transfinite induction on the height of derivations. And the bound on the ordinals that we need for the transfinite induction, we can always bound our proofs by a tower of omegas. So the bound on the ordinal we need is the smallest ordinal that's greater than any such tower of omegas, and that's called epsilon 0. So formalizing the proof, let's put it at the bottom of the board so I don't need to clean the board. We get that if we add to PA a principle called transfinite induction up to epsilon 0, then we prove the consistency of PA. So we've identified exactly the combinatorial principle that we need for proving the consistency of PA. But how can we add transfinite induction up to epsilon 0 to arithmetic? I mean, arithmetic's about the natural numbers, and here we're talking about ordinals. Well, transfinite induction up to epsilon 0 says that is the schema that for any alpha less than epsilon 0, we have the induction principle that if for all beta less than if a formula A that we're looking at is progressive in the sense that whenever it holds for all beta strictly less than alpha, it holds for alpha itself, then alpha less than epsilon 0, A holds for alpha. So that's the transfinite induction principle. We need to encode this using natural numbers, but actually epsilon 0 is a countable ordinal. So it can, in principle, be encoded by natural numbers. And in fact, there's a very nice way of doing it using a notation called Cantor normal form for ordinals. And so one encodes Cantor normal form for ordinals using numbers, which is actually a primitive recursive encoding. Everything that's related to the ordinals up to epsilon 0 just uses primitive recursive functions. Then one can state this axiom schema, transfinite induction up to epsilon 0, and if we add it to Peano arithmetic, we can prove the consistency of Peano arithmetic. Moreover, epsilon 0 is the smallest ordinal for which this schema is not already provable in Peano arithmetic. We reduce the ordinal, then it is provable in Peano arithmetic. Okay, so that's everything for today. Thank you for your attendance during the course, in spite of the neprijetna ura for the lectures from all sides. If you do have time to stay for an extra 10 minutes or so, maybe I'll say bye-bye to people watching on the video.